After seeing in a previous video that pitchblende or uranium ore can be found in Saxony and on the German-Czech border, I wanted to make another video about other non-radioactive minerals that can be found in Saxony. In Antonstal, in addition to radioactive minerals, I also found this chunk here, which was just sticking out of the ground. Marvin had a UV lamp and a very nice LED magnifying glass with him, which allowed us to take a closer look at the rainbow mineral.
Kriegt man das so auf? Ja.
Oh,
Der hat richtige Strukturen da drin.
ja, schön.
We also found a related mineral there. Any ideas in which mineral I'm referring to? In Johann Georgenstadt there was another slag heap that had been filled with sand, but even there I was able to take a very large specimen of an amethyst with me. A chunk with quartz crystals and a few others. After some cleaning etc. we had a very strong suspicion as to what this rainbow mineral might be. But I'm allowed to analyze at the university, and luckily I have received support from Professor Dr. Gregor Starr. He is from the Department of Classics and has a handy X-ray fluorescence camera. Fortunately, it is really easy to use. Point the camera, adjust until the laser points overlap and go behind the radiation shielding. And then just start measuring. After the measurement we get a X-ray spectrum from this mineral. In this case, for this mineral, you can see from the luster that it clearly has to be pyrite, also known as fool's gold. If you look at its composition and structure in the literature, you can see that it's chemically described as an iron 2 disulfide. This is a somewhat advanced structure as we have a more exotic disulfide ion in where the sulfur has an oxidation state of -1. And these dumbbell-shaped ions are surrounded by an octahedron of iron 2 plus ions. That was a lot of information about the structure. Which of these information can we obtain from the XRF spectrum? That the sample contains the elements iron and sulfur. Here they are helpfully labeled as sulfur K alpha, sulfur K beta, iron K alpha and iron K beta. In this case, XRF analysis involves irradiating the sample with Bremsstrahlung over a broad energy range. Inner electrons are knocked out of the atom of the sample and the electrons above them fall down to the now vacant level and release the energy difference in the form of radiation, usually very characteristic X-rays. I formulate it like this because in order for us to see an element in the XRF at all, it must have more than one shell, so hydrogen and helium are out, and the transitions to the innermost shell must lay in the X-ray range, which also unfortunately rules out all of the elements of the second period, i.e. lithium to neon. This rules out all of the classic molecules, leaving only the salts that contains elements of the third, fourth and fifth row, for example. Organic molecules mostly use the first and second periods. Starting with sodium, but realistically only from aluminium onwards, the first transition in the spectrum can clearly be identified. What I have marked in green here are the elements whose K-alpha line is within the measurement range of the XRF camera. Theoretically, it could go as far as praseodymium, but with barium you reach the limits with a K-alpha energy of 32.19 kiloelectron volts. In general, the higher the proton number, the higher the K-alpha energy. The K-beta and K-gamma lines are even higher in energy. There is also a new nomenclature for this. Alpha only describes the shell directly above it, and above the K shell is the L shell. So according to the newer UPAC nomenclature, it is called the KL line. But since almost all literature still uses the old nomenclature, I will stick with this for this video as well. The L-alpha lines are lower in energy than the K-alpha lines. And these now also enable the analysis of other elements up to uranium. Its L-alpha lines are at 13.61 kiloelectron volts. The device can display lines quite well, starting at 2 kiloelectron volts. This makes zirconium the first element whose L lines are already high energy enough for the XRF measurements. Back to our minerals. All the chemistry that then ensured that we have disulfide ions and so on takes place at the valence shell, which is not really in interest for us during XRF measurements. This means that although I could see from the K-alpha line that sulfur is present in the sample, I cannot make a statement about its chemical form. So you kinda have to approach things with a bit of chemical intuition and then say, okay, if iron is present, it stands to reason that sulfur is negatively charged, but strictly speaking, that's just a guess. Strictly speaking, it could also be a sulfate ion, and we don't see the other 4 oxygen atoms bound to it, because we can only see elements from aluminium onward. The compound FeS and FeS2 would look identical in this spectrum. But wait a minute, there are percentages down there. 76% sulfur and 23% iron. That would perfectly reflect the atomic proportion of the 2 elements in a sample for a composition of FeS2. Caution is advised here, as the X-ray lines of iron are much higher in energy than those of sulfur. This means that we can look much deeper into the sample with the iron XRF lines, as higher energy radiation passes through more of the sample itself. In this case it fits very well, but I would rather be cautious in this case. The device cannot have an appropriate correction factor for every energy of every material. Now let's take a look at the rainbow mineral, and with the information we have, we can see that the crystal contains copper in addition to sulfur and iron. With a little mineralogical knowledge, it is obvious that this is the copper version of pyrite. This is called chalcopyrite. It has the composition CuFeS3. For example, XRF can be used to rule out the possibility that this is a bismuth crystal. That would also be very unlikely in nature, but here is definite proof with the XRF spectrum. Among other things, we also measured the purple part of the mineral, which only shows metals and chloride. But chloride in such small quantities, this is where things get quite tricky. Okay, under the microscope and with geological knowledge, you can deduce that this must be purple fluorite, but you can't prove it using XRF because the element fluorine, which is present here as a fluoride, is not detectable in XRF, as it's again an element of the second period. No chemical form of this element can be visible in the XRF. It becomes much clearer with this beautiful fluorite single crystal, where you can clearly see from the cube shape that this must be fluorite and not quartz. And here you can only see calcium being displayed. If you look at this specimen a bit more closely under the microscope, you can see very dark spots everywhere in this purple colored crystal. These are called radiation halos. So there is a tiny bit of uranium enclosed, and the alpha radiation of the uranium and its simultaneously enclosed decay products has caused radiation damage to the crystal lattice directly around it. This leads to a very dark coloration. So I did smuggle a bit of radioactivity into this video about non-radioactive minerals. It's absolutely fascinating to be able to see something like this. I will go into more detail about this in another video. In this specimen of a quartz crystal, you would not see oxygen, only silicon. So this fluorite CaF2 and this quartz SiO2 can be distinguished by looking at the crystal form. And you can also classify them quite well with an XRF based on calcium or silicon lines. But with minerals like this, you still need a good knowledge of minerals. This means that these two would look identical in the XRF. Amethyst and quartz are both silicon dioxide based minerals. In amethyst, we have a minimal iron impurity, which when oxidized by ionizing radiation causes a purple color. It was quite easy to see as to why it is so pale. It must have been laying in the sun for quite some time before I found it. Amethysts lose their color when exposed to strong sunlight or heat. They then would become more yellowish and are referred to as citrine. And I found all of these minerals in Saxony. A huge thank you goes out to Professor Dr. Gregor Stab from the Department of Classics for letting me do the analysis, and to Marvin, Paul and Niklas for coming along with these trips, as well as to my patrons for their financial support. With that being said, thank you for your attention and goodbye.